We're going to continue in physiological optics. In this series of videos, we're going to shift our focus and begin our review of contact lens. In this session of contact lens, we're going to primarily focus on vertexing contacts and the lacrimal lens power. However, before we can get there, we need to talk about one topic, and that's going to be back vertex power and how it relates to contacts. So let's look to the text. So if you look in the text, you guys will see the back vertex equation there. Now, the only time you need to use this equation with contact lens is in the situation where a contact lens thickness is given. Okay? For the most part in contact lens, we're going to assume that the contact lens has an infinitely thin thickness, right? That it doesn't have a thickness that we have to take into account. However, if you get into a question where you think, okay, this is a contact lens and they're giving me a thickness of the contact lens, I want you guys to think automatically, okay, I'm going to use the back vertex power. Right? Same equation that we've used before. For those of you guys that like P's instead of F's, then just draw that F and make it a little bit of P there. Right? Remember that thickness has to be in what unit? That's exactly right, meters, right? So you want to write meters right in there. Good, let's keep on going in the text. You guys have an example of 5.24 I'll let you guys work through that walks you through exactly that, having a contact lens with a thickness using the back vertex equation. Now let's get into the topics we really wanted to hit, which is going to be vertexing first and then getting into lacrimal lens power. So remember guys, why do we have to vertex contacts again? That's exactly right? We're bringing back some geometrical optics to this, right? Effective vergence or downstream vergence, right? You remember that whenever we take a lens, right, and we move it closer towards the eye, what happens? Yeah, it becomes effectively what? More minus in power, right? So we have to compensate for that by doing what? Always making the contacts more plus. That's exactly right. So whenever you're vertexing for contacts, right, if you get a contact lens prescription that's more minus than the glasses, right, then you did something wrong, right? We're always going to be more plus in the contacts than we are in our glasses. And if you guys see that, that's going to be boxed right there in the text. You want to put a highlighter around that box, right? It says for both plus and minus lenses, more plus is required whenever you correct the patient in contacts. Now, it all has to do with effective vergence. You have the equation there again for you, right? So just remember that whenever you're looking at that equation, that power of the contacts equals the power of the glasses over 1 minus the distance. That's going to be the vertex distance, right? That's got to be in meters, right? So remember to convert that from millimeters, which it'll probably be given to you, to meters. Awesome, guys. So then you guys have that example 5.25 that walks you through doing the vertex calculation as well. All right, now let's get into a topic of lacrimal lens. That's what we're going to primarily focus the rest of this session talking about is GP contacts and how it relates to a lacrimal lens, right? So if you guys look, what's the key thing to remember about GP contacts? Yeah, the key thing to remember about GP contacts is that they create a lacrimal lens or a tear lens between the contact lens and the cornea, right? And unlike soft lenses, we have to account for this lacrimal lens or tear lens that's created whenever we correct for a patient, right? So if you guys look in the text, you guys are going to highlight that under lacrimal lens or tear lens, and I'm going to use them interchangeably, and I want you guys to be able to do that as well, right? Is you want to highlight the second and third sentence there, right? The lacrimal lens has a certain power that is dependent on the front surface of the cornea, the back surface of the contact lens. We'll get into that more in just a minute, right? And the lacrimal lens power must be accounted for in prescribing GP contacts. So how do we account for that in prescribing GP contacts? That's going to be the GP contact lens equation. Let's take it to the whiteboard. So in order to account for our lacrimal lens or our tear lens, right, we have this equation 5.62 that I like to call the GP contact lens equation. So I would suggest you guys writing it out there at the side. It's kind of a header to kind of name this equation. So whenever we use it in the future, if you hear me say GP contact lens equation, it's exactly what we're talking about. Now you guys have in your book FLL plus FCL plus FOR equals RC. Well, I think it's a simplified way of kind of thinking about this, and that's just to write out what the equation stands for. And what that means is that right here, right? So the power of the lacrimal lens plus the power of the GP contact lens plus the power of an over-refraction, if there's one present, right, has to equal the corneal plane refraction or the vertex power at the cornea, right? Or some of you guys know that as the vertex spectacle Rx, okay? So we're going to use this contact lens equation throughout our GP contact lens problems to help us understand and be able to account for the lacrimal lens power. Now let's go on and talk a little bit more about the lacrimal lens power. How do we determine the power of the lacrimal lens or the tear lens? Well, let's take a look at this picture. I think hopefully this will help kind of illustrate this point, right? So we've got a GP contact lens, our tear lens, and also we've got the cornea with the patient's eye, right? So if we look at the front surface of the tear lens, right? What is that front surface of the tear lens? What shape is it going to match? Yeah, it's going to match the shape of the back surface of the GP contact lens, right? And what about the back surface of the tear lens or the lacrimal lens? Yeah, it's going to match the shape or the curve of the cornea, right? So if you look in your text, right, we'll see that the back surface of the lacrimal lens or the tear lens has a radius of curvature that is equal to the radius of curvature of the cornea. If you look at the front surface of the lacrimal lens, it's going to have a radius of curvature that's going to match the base curve radius of the GP contact lens, right? So now, whenever we look at moving further into this thought process, okay, whenever we think about the tear lens, right, what index do we think of with the tears? Yeah, we think of an index of 1.336, right? What about the cornea, right? What kind of assumed index do we use do we think of for the cornea, right? We talked about this with keratometry, right? 1.3375, right? Do you guys realize how close those two numbers are to each other? Yeah, exactly. So what that allows us to do is that allows us to be able to say, okay, instead of using the tear lens index, right, and the cornea index separately, what we can do is we can say, okay, instead of thinking of the tear lens as having an index of 1.336, we can think of the tear lens and the cornea as having the same index, and we're going to use 1.3375 to calculate the power of the tear lens, right? And if you guys look in your text, you'll see that, right? In theory, we use the index of refraction of the tear film was 1.336, right? And then you also see with keratometry there bolded a couple lines underneath that, you'll see calibrated using an index of 1.3375 as the effective index of the cornea, right? So now how are we going to calculate the back and front surface of our tear lens? What equation are we going to use? Yeah, that's going to be our power equation, right? We've used it several times throughout our lectures, right? F equals N2 minus N1 over R, right? Now, if we use an index of the cornea here for our N2 and then we use air for N1, right? Then what we're going to do is we're going to have a power equation that's going to look like this. It's going to have 1.3375 minus 1 over the radius, right? Let's make that 5 and minus sign look a little bit better for you. There we go. All right, so 1.3375 minus 1 over the radius. Now remember, the power equation uses the radius in what units? Yeah, that's going to be meters, right? So that equation can simplify down to this equation we have in the book, right? Which is going to be 0.3375 over the radius in meters, right? And that's what we have in the book here for you guys to use. So for the equation 5.65, what you guys want to write there, we say 0.3375 over the radius, you want to write in meters right there, right? Meters right there. Now, one extra step in simplification of these type of problems is that we can even say, okay, instead of thinking about the radius in meters, right, why don't we just keep it in millimeters, right? And so that's going to simplify this down to F equals 337, right, 0.5 over the radius in millimeters, right? And so this is the equation that I'm going to use as we're moving forward working all of these problems, right? Because I think it is the simplest equation for us to use to calculate the power of the tear lens, right? And so you guys want to write that in your text. And this is, if we're going to use this equation, this is going to be number 3 in our toolbox of equations that does not use meters, right? Because if we use everything in the radius in millimeters, that's going to be how it's going to be likely given to us in a problem, right? If we use the equation in the book that uses meters, then we're going to have to do one extra step in converting from meters to millimeters. Now, does it make a difference which one you use? Absolutely not. I would just pick one of the two, whichever one makes the most sense for you, right? And be consistent so you can make sure to dominate these questions. Okay, so now let's think a little bit more about the GP and tear lens relationship, right? And so what happens if I have a GP contact lens, right, that is the same curvature as the cornea? Yeah, what's going to happen if I have the GP contact lens with the same base curve as our cornea? What's going to be our lacrimal lens power? Yeah, it's going to be 0, right? Our lacrimal lens power is going to be 0. And you want to highlight that in your text. Right, that's that first bullet point there in the text which says if a base curve of the contact lens equals a corneal curvature, right, go down 2 lines, lacrimal lens power will be 0. Excellent. Now, what happens if our GP contact lens is steeper, right, than the cornea? What kind of lacrimal lens or tear lens is going to be created? Yeah, it's going to be a plus powered tear lens, right? So let's highlight that in the text. So if you have a contact lens that's steeper, right, then right below that, total lacrimal lens power will be plus. right? Because the contact lens will vault up off the cornea until it's going to create a tear lens that's going to be thicker in the center than it is on the periphery, and that's going to create effectively a plus powered tear lens. What about if our contact lens is flatter than the cornea? Yeah, what's going to happen there is that we're going to have less tears in the center, more tears in the periphery, so we're going to create, in effect, a minus power, right? So if the contact lens is flatter than the cornea, we're going to get a total lacrimal lens power that will be minus. Excellent. Let's move on and finish up this topic working example 5.26 and 5.27. So the following information is obtained from a patient, corneal K readings of 7.5 millimeters or 45 diopters. The subjective refraction at the cornea is +1. What power of contact lens should be chosen for an on-K fit? Why don't you take a second, pause the video, work the problem, and then we'll come back together. So to solve this problem, the first thing we need to do is look at what is an on-K fit. Right? What does that mean? That means that the base curve of the contact lens matches the base curve of the cornea, right? They're equal to each other. So we just got done talking about if we do that, what does that make the tear lens? That's going to make the tear lens equal 0, right? It's going to make the tear lens equal 0. Now, let's work through this thought process using the GP contact lens equation so I can kind of show you an example of this before we get in a little bit more difficult example in 5.27. All right, now, whenever you write out the GP contact lens equation, what I typically like to do is do everything in power crosses, and you'll see that here at the bottom of your screen, right? Now, in this problem, we have a completely spherical cornea, right? But if you have a toric cornea, it gets really complicated really fast. So if we work it the exact same way, you'll be able to dominate those more difficult type questions, right? That's going to be using power crosses. All right. So first off, what's going to be the power of our lacrimal lens? Well, we said that tear lens or lacrimal lens is always going to be 0, right? So we're going to put 0 on both aspects of our power cross, right? Now we're trying to figure out the power of the GP contact lens, right? This is what we're trying to figure out from the problem. It's asking us what power do we need to choose so this patient can see correctly. Our over-refraction, right, is not given in the problem, so we're going to put in a 0 there, right? Just as kind of a placeholder, right? And the power of the eye at the cornea, right, or the vertex spectacle Rx, right, the subjective refraction at the cornea is going to be +1. Now, in a problem, it could give you their spectacle Rx, right, and a vertex distance, and it adds one level of complexity to this, right? That'd be a way to stretch this concept. And then in that case, you would use the vertexing equation to actually vertex that power, figure out what the power at the cornea is, but either way, once you get that number, you're going to put it here. So +1 here. Right? Now, if we look across, since we have no lacrimal lens and no over-refraction, then simply the power of our GP contact lens is going to be chosen for the power of our cornea, right? So +1 is going to be the power of our GP contact lens, right? This is the case where there's an on-K fit with no over-refraction, then that means simply the power of the GP contact lens is going to be equal to the corneal plane refraction. Now, did you need to go through and work out this problem the way we did? No, not necessarily. You probably looked at this and thought, hey, Ryan, this is an on-K fit. I know lacrimal lens is 0, so the power of the GP contact lens is going to be chosen for the subjective refraction of the cornea, +1. Awesome. I'm glad you're dominating this material. Let's move on to example 5.27. You decide to flatten the GP contact lens now of that same patient as before. You still have a corneal K reading of 7.5 millimeters. Subjective refraction at the cornea is still +1, right? But now it's asking what power of GP contact lens is required if you now choose an 8 millimeter base curve to get a better fit for the patient. Hold on, don't work this problem yet. Across the nation, there's about 6 different ways to work this problem, but I want to show you a method that I think is simple and easy. Okay, so check this out. So working this problem, the solution that we have in the book is one method of working this problem out. It's kind of like an academic way that walks you through calculating the back surface tear lens power, the front surface tear lens power, adding them together, and then working out to get your final answer. And like I said, there are at least 6, maybe more ways that I've seen this problem worked with students in the past. But what I want to show you today is something that's not in your book, but I feel like it's an easy way to be able to attack and dominate this problem, okay? So it's going to be the 3-step method to do GP contact lens problems, okay? So I'm showing you the first step here. The first step is that we're going to convert everything to diopters of the cornea, right? That's going to be that equation we just used, F equals 337, right, 0.5 over the radius in millimeters, okay? So that's going to be our first step, right? So the first step is you convert the cornea and the contact lens to your power that's going to be in diopters, right? Now, second step, once you've converted everything to diopters, your second step is to calculate the tear lens, right? So how are we going to calculate the tear lens? We're going to take the base curve, or the GP contact lens base curve, right, in diopters, subtract the cornea base curve in diopters, and that's going to give us our tear lens power, right? And that'll give us either a positive or a negative number based on whether the contact lens is steeper or flatter than the cornea, and you'll get that for your tear lens power, all right? Now the third step is going to be to solve the GP contact lens equation, right? For whatever variable that it's asking for, right? If it's asking for the GP power, you're going to solve for it like we did in the previous example. If it asks for the overfraction, you could solve for the overfraction. If it asks you, okay, it gives you the overfraction, the tear lens power, and the GP, and it says what is going to be the power at the cornea, you could solve for that as well, all right? So our last step, we're going to solve the GP contact lens equation. So like I said, not in your book, but I want to show you what I think is an easy way to be able to attack and dominate this question, all right? If you don't like this and you guys learned it a different way in your class, fine. I want you guys to do it the way that you guys learned it, whatever method you think is the easiest, and it's going to make sure that you dominate these questions whenever you move forward with boards. That'll make me happy. So whenever I'm attacking example 5.27, the first thing I'm going to do is I'm going to convert everything to diopters, right? So I'm going to take the power, the GP contact lens base curve, I'm going to take 337.5 over that 8 millimeters, right? So remember, I keep everything in millimeters, right? And that's going to give us 42.19 diopters for our base curve of our GP contact lens. For the cornea, we're going to take 337.5 over 7.5 and get 45 diopters. All right. So now we've done our first step in our three-step method, convert everything to diopters. Next, we're going to move to step 2, right? And in step 2 is you take the GP base curve, you subtract the corneal base curve, and that's going to give us our tear lens. So in this example, we're going to take 42.19, we're going to subtract 45, and we're going to get minus 2.81 horizontally and vertically. Now, once again, guys, I would suggest doing power crosses for this. Now, in this example, you didn't necessarily have to do a power cross. You could have just subtracted 42.19 minus 45. But let's flash forward and think about stretching this concept that you guys are going to see on quiz questions and the SMART test, right? In that you're going to have maybe a toric cornea or a toric contact lens, and so it will make things a lot easier with working with astigmatism if what you do is you work across the horizontal, right? So you take 42 minus the 45 across the vertical, right, to get minus 2.81, and then you work across the horizontal the same direction and you get a horizontal power, right? So I think using power crosses makes things simple. So I would go ahead and just do that now, even if it's a spherical situation like this one is, because if you do it repetitive like that, it's going to make it easier for you whenever you see a more difficult problem or a stretched concept. Now for our third step in this method, right, we're going to solve for the GP contact lens equation. So the GP contact lens equation, remember, is the power of the tear lens plus the power of the GP contact lens plus the power of the overfraction equals that vertex corneal plane refraction. Now this example is asked, or this question is asking for the power of the GP contact lens, right? So we're going to rearrange the equation. So we're going to take the back vertex, or not the back vertex, but the spectacle vertex Rx, right, or the corneal plane refraction, minus the tear lens, minus the overfraction, and that's going to give us our final answer, right? So now I'm going to pause the video. Why don't you guys work out this last step with the power crosses, and then whenever we come back, we'll work it together. So to solve this final step, right, we're going to put in +1 for our vertex spectacle Rx prescription, right? +1 and +1 here across the vertical and horizontal. We put in minus 2.81 in the vertical and horizontal for our tear lens power. And then, of course, like I said, we don't have an overfraction here, so you don't necessarily have to have this in there. But I go ahead and work it like this, so that if there was an overfraction that was given, you could put that in there if you needed to. So what's going to happen here is we're going to get minus a minus, right? So whenever we look at our final prescription for the GP contact lens, we're going to get plus 3.81 and plus 3.81. So in this case, once again, it's spherical. So our final answer is going to be plus 3.81 diopters would be our new GP contact lens power that we would need to use to be able to perfectly correct this patient if we adjusted their base curve of their contact lens from 7.5 millimeters to 8 millimeters. So hopefully this made some sense for you guys. Like I said, for me, this was like a big moment whenever I looked at this and thought, okay, maybe there's a simple way, because I always was really confused working this example. It's a really challenging one because there's so many ways that I've seen it worked. And anyways, I just, whenever I was working through this, seemed to make some sense for me. But once again, if you guys work this a different method and it makes more sense for you guys to do that, That's what's going to be best for you. All right, guys, keep on working hard. Go dominate the quiz, and I'll see you on the next video.